matrices. But we tend not to say, I think we tend not.
The word in a random way?
Yeah, I think random matrices is to be, yeah, exactly, that's what, yeah, I think that's it, exactly. I just wrote again what we did last time, so if you have any question about the setting, the notation, and I rewrote the example that I was asked during the questions about how we use the Furstenberg formula, lambda Lyapunov exponent, how we compute it using stationary measures. And I was asked how I use this formula to compute to show that the Lyapunov exponent of this degenerating set, the example of Kiefer, was 0. So do you want me to explain it again? I mean, really, yeah, okay. Okay, so Lyapunov exponent is you take this set of all probability stationary measures on the projective space, measures on sphere which are invariant under the semigroup, but on average with respect to the probability measures. I take all the probability measures here and I compute a double integral, and I take the biggest one, and it's a max, it's part of the theorem. And moreover, we are saying that it's a maximum of quantities that depend on your initial mu, which are the weights on the generating sets, and that depends on the stationary measure. I will call it lambda mu nu. And moreover, a remark that will be helpful is if the semigroup generated by your support is irreducible, which means does not fix a proper subspace of Rd, so there is no lines which are fixed by all the matrices, neither planes, etc., then they may exist many stationary measures, however, this quantity does not depend on the stationary measure. Example, head and tail with rotation, diagonal matrix, and I choose J with probability very small but yet positive, and 1 epsilon A. Let us compute the Lyapunov exponent and show it to be equal to 0. First of all, algebraic remark. It's true that this semigroup of matrices permute 1, 0 and 0, 1. However, it acts irreducibly. There is no one line stabilized by all these matrices. Hence, I can apply this remark, and it's enough to choose one stationary probability measure and to compute this quantity. By irreducibility, it's enough to find one stationary probability measure and just to compute this double integral. Now, since I permute E1 and E2, the Dirac mass, the uniform probability measure on E1 and E2 is invariant under A and under G as matrices. Hence, it's invariant for any choice of weights. So it's mu stationary. Let us compute this quantity, the double integral. So the double integral with respect to a product measure mu of G and nu. So I chose 2. So epsilon, 1 minus epsilon is the integral with respect to mu epsilon. So it's a double integral. The sum here is when I'm integrating with respect to mu epsilon. And now this is an integration on the projective space. So I'm just computing this double integral. Okay? Now, nu is just, it has atoms, 2 atoms. Now when I integrate, J acts by isometry, 0. So now, this is A, this is the fixed matrix A. Nu is half-half. So, it's half log of A acting on E1, so it's log lambda, and half A acting on E2, which is 1 over lambda. So it's 0 independently of epsilon. So it's 0 for any epsilon. Hence, there is no continuity of Lyapunov exponent, because by degenerating the support, I obtain a Dirac mass on A whose Lyapunov exponent is len lambda. So is this clear? This is the actually there is no other invariant stationary probability measure, but I just wrote what I need in order to compute it. I said that it's enough to find one. By irreducibility, it's enough to find one. That's actually the same. It's the only one. Okay. We can prove later that it's the only one. So my goal, I didn't start my lecture 2 in my outline. So I'm just continuing the previous lecture. It will take me some time. Now I want to prove this theorem. Okay? So proof. Do you want me to do the proof? Proof. Okay, let's start with the easy, let's say. Easy inequality. So that lambda is bigger. Lyapunov exponent is bigger than any, I will call it cocycle average. It will be clear from what cocycle later. For any mu, which is mu stationary. So this is this is the goal. Now, so let mu be mu stationary. Let V be a vector, non-zero. And I will compute log of the random walk acting on V, the growth of the vector. And I will write it as a Birkhoff sum. So the goal is to use the Birkhoff ergodic theorem, and I will interpret this quantity as a Birkhoff sum. How? By telescoping. So this is the first step of my class. So it's a recursive formula. I divide and multiply by the same quantity. And here, Bn is just one increment, okay? It's with respect to mu. It's acting now. This is independent of the direction by V, scale V by 2, here by 2. So it's a quantity that is on the projective space. So this is just Bn minus 1, B1 acting in the direction V. In some sense. I mean, it's a quantity that depends only on the action on the projective space. By iterating this formula, we obtain a sum and without loss of generality, I took V of norm 1, so that I do not have the last term, and B0 is identity by convention. So I obtain this telescopic, this sum, that I will write it, so define sigma G from Gx to x, that take any matrix, any direction, and take the logarithm of the norm of GV divided by V. It's a well-defined, independent of the choice of the director vector V of the line. Hence, this is sigma of bi acting on here. It was not clear what I meant. I just want to be here. Here, let's erase this, and now everything is clear. Okay, and sigma is a cocycle. I mean, a remark. I don't think this is called. This is a cocycle. This is an additive cocycle, in the sense that sigma GHV is sigma GHV plus sigma HV. So if you want, all of this is sigma Bn B1 V that I wrote. I mean, using this, I'm just rewriting my telescoping sum in a more formal way, writing this as sigma Bn B1 comma V, and using the property that this map sigma is a cocycle, immediately gives this sum. And now, I used always the dynamical system, the Bernoulli shift, but here there is something skewed happening. I will define a new skew product dynamical system. B hat, which is Bernoulli, which is B, which is G to the power N, times the projective space. How I will act on it. I take an infinite sequence. I take a point X. I shift. And then I remember my first coordinate. And I act on the projective space. So this is B1, no. This is B2, no. So this is a transformation of my product set, but with a skew dynamics, in the sense that there is some dependence. And let's iterate T hat. Let's iterate T hat. Observe that. Let me just say that I will endow it with the product measure, Bernoulli times the stationary measure, mu, that I already fixed from the beginning. Observe that T hat to the power n of Bx is Tnb, usual shift, and here it will be Bn minus 1, B1 x. So this is my random walk acting on X. Okay? And hence my sum can be written really as a Virtzer sum. Where f of Bx depends just on the first coordinate, sigma B1 x. So I wrote the logarithm of the norm of the random walk, the product of the matrices Bi acting on V as a sum of a Birkhoff sum, as a Birkhoff sum, sorry. And a remark, and this gives a new way of thinking, another way of thinking of stationary measures, saying that mu is mu stationary is the same as saying that the product measure, Bernoulli 10 times nu, is T hat invariant. And this really follows from the definition. So this is one point of view of stationary measures. So I have a skew product dynamical system. I'm finding, and I have a transformation, I'm finding invariant measures, but not any invariant measures that project onto the first coordinate, onto the Bernoulli measure. I'm not interested in the invariant measures for this transformation, no. I want the ones that fibers above the Bernoulli measure, mu fixed. And the same hold slash ergodic. And now we're happy. By Birkhoff ergodic theorem, I will obtain that for Bernoulli times nu almost every infinite sequence B direction V, len Bn B1 V over n converges to a number. And what is this number? It's the integral over my new dynamical system f of B V d mu n B d nu V. And what is this integral? By definition, it's a double integral of f of BV is sigma B1 V d beta of B d nu of V. Sorry, I will not write here anymore. Let me write it here. So the right hand side is equal double integral sigma B1 V d beta of B d nu of V. But since my cocycle is locally constant, so it's enough to integrate over the first coordinate, which is mu. I'm integrating just over the support. Which is just, by my definition, this double integral I considered from the beginning. B1 is the first coordinate of the infinite sequence. It's a matrix in the support of mu. So I obtained there, but this is clearly, its lim sup is less than the Lyapunov exponent. The Lyapunov exponent is the growth of the matrix itself. So I obtained that this is less than that, which finishes the proof. But left-hand side, lim sup of left-hand side is less than lambda, Lyapunov, of mu, Lyapunov. So it gives the first direction. Okay. Now let's go to the other direction. I don't think I will prove everything, but I will, prove something at least to have an understanding of, to understand that something is going on, at least.
Sorry.
Yeah.
Can you repeat what it means that mu is mu ergodic?
Yeah, in this context, yeah. The simplest thing is to say, I cannot write it as a convex combination of stationary probability of the same without ergodicity. I cannot decompose it into a convex combination of stationary probability measure. And in the point of view of group actions, it's the same as saying that nu G inverse A, if G inverse A equal to A for any G in gamma mu, then u of A is 0 or 1. if you have a set which is invariant, but it has under the group, the semi-group of transformation, it should have mass 0 or 1. And it's ergodic with respect to the skew product dynamical system, really in the usual sense. Now the other direction, I want to find a stationary measure attaining the Lyapunov exponent. That's the other direction. So let us define F. So if there is no stationary measure fixed, I want to construct something. Set of non-zero vectors such that almost surely lim sub Bn B1 V over n is less than the top Lyapunov exponent. I take the set of all vectors such that when I do a random walk, they have the bad contraction behavior, the bad gross behavior. So the Lyapunov exponent is the almost sure limit of the exponential growth exponential growth of the matrix knonw. I take now the vectors which have smallest growth in some sense. And here really quantifiers are important. So small v belong to F means there exists a full space of probability of measure 1 for the Bernoulli shift, but it depends on V. Okay? But I'm just saying this because if people know oscillator theorem, it's really an opposite way of thinking. I'm not fixing a trajectory and seeing how my vectors behave, no. I'm fixing a vector and then doing my random walk. So the almost surely here, the set of full probability measure depends eventually on V. Okay. Observation 1. F is a subspace. If you take two vectors, if the exponential growth is less, so if you have
logarithm, not missing a logarithm at the right top corner. Limit, after the limit. Log.
Yes, thank you. Thank you. First of all, it's a subspace. Second, it's proper. By choosing a basis. Because I know that the Lyapunov exponent is the exponential growth of the matrix. So at least you will have one vector in your favorite basis that will have a good exponential growth. Second, it's T-mu invariant. It's invariant under the semigroup of transformation. Why? If I take Bn, B2, B1, V, so let me do the proof. Let V be in big V. I know that almost surely log of Bn, B2, B1, V over N in soup is less than lambda 1. And the distribution of B2 when I shift has distribution also mu to the power n. So this will tell me that I can write it, and B1 has distribution mu as a random variable. So I can say that for mu almost every G, for beta almost every sequence B, that now I started in B2, log of Bn B1V over n is less than lambda 1 lim-sup, which amounts of saying for mu almost every G, B1 GV. GV belongs to F. So I'm just saying that if I shift my Bernoulli sequence, it has the same distribution, mu to the power n. And B1 can be any element in the support. That's what I am saying. And since the set of element G such that GF is in F is closed, in G it contains the support of mu, stabilize F. This is a vector space, and I can iterate all the semigroup generate F. So, the set of vectors whose exponential grows along a typical infinite sequence is less than the real growth is a proper invariant subspace. In particular, if I'm acting irreducibly, this space does not exist. In particular, it's zero. I mean, I said non-zero, yeah. The space does not exist. I can, without loss of generality. Yeah, let me just put it like that. This is well defined, and zero belongs to it because by convention it will have minus infinity. I'm sorry. It was not so. This has a meaning, and so if gamma mu acts on RD irreducibly, F is zero. So let us have in mind irreducibility, then I explain the case irreducible but F zero yet. I mean, this can happen. But what do I gain? So case one, which is the case I will explain. Let's understand what happened when F is zero. Example, irreducible. What does it mean? It means for every vector in Rd minus zero, this does not hold, all this property does not hold almost surely, which means there exists beta 1 in my fruit shift of probability of positive probability, let's say, such that for any b in beta 1, for any infinite sequence, the lim-sup is lambda 1.
1 over n.
As usual, thank you. I should forget something, either log or what. I mean, the negation of almost surely is not, it doesn't mean that there is a full probability, there is a full set of full probability such that the equality is here. But actually, it's true that almost surely it holds, but it does not follow logically from the negation. What I'm saying is that finally, remark, we can prove that this holds almost surely, but I cannot prove it from here. And actually, the lim sup is a limit. But I mean, all of this does not follow immediately from what I'm saying. Okay, what do I gain from here in terms of stationary probability measure? Now take a stationary probability measure. But I know that by the Birkhoff ergodic theorem, this converges to this double integral. So this holds for any b, right? For any vector. So if mu is mu stationary, then for mu n times nu almost every b v, this is this double integral, okay? So I take a generic vector v with respect to nu. And so by combining this information, it's true that b1 depends on v. And by combining this information, now I fix the stationary probability measure. We have so what I was doing is proving then when we have irreducibility, there is one cocycle average. Now a little bit slightly more difficult, I mean not so much, but I will not do it. It's what's happened when f is not 0. Okay? I mean we prove, this what, for instance, when proving the example of, we're doing the solution for Kiefer's example, this is enough what we did. When we computed Lyapunov of mu lambda, because this example was irreducible. But the full picture, let me just tell you what happens if f is not 0. What does it mean f is not 0 concretely? F is a subspace invariant. So by all your matrices, so by choosing a suitable basis, my matrices are of this form. Where they are upper triangular biblock. And here, this is the action on F. All my matrices in the support are like that. And when doing the products, when I do my product, so I'm introducing also the reducible case. This is a reducible setting. When doing my product, here I will have a product, a random walk here. Down I will have also a product which represents this is the action on the quotient vector space. There is since f is invariant, there is a natural action on the quotient. I mean, with matrices it's clear. And here it's the unipotent parts are really the complicated thing, right? It's a sum. And saying, yeah, this is what we need to handle in the reducible case. Yeah, I agree. So, but just now on this level, what does it mean f non-zero? It means when the exponential growth of this is much, much less than the total. Okay? Just some examples.
Would you prove this part too?
No.
Because this is what I know as Furstenberg theorem, that Lyapunov exponent is not 0.
No, maybe. Okay, Furstenberg theorem, the Lyapunov is non-zero, it's under irreducibility. Yeah, which are not here. which are on the irreducibility setting.
Yeah, but did you prove it or?
No, no, I didn't prove it. I will give just intuition later, maybe when I speak something. Okay, and just remarks. We can prove that the Lyapunov exponent is actually, so if you look at exponential growth, it's enough to look at the diagonal part. It's enough to look at two, because it's exponential growth. Lyapunov exponents are exponential growth. In our head, this will go maybe, can be bigger, but not at the exponential rate. And and what do we have in this case? This is a random walk here on a smaller subspace, and this one verifies F0. I cautioned out by it. It means that all vectors here will have the same exponential growth. Maybe they are not irreducible, but they will have F0.
So sorry, just the first remark, are you saying that if you have a, say, L1 upper triangular valued skew product, a block upper triangular valued skew product, the exponential growth of the norm of this block upper triangular matrices are given by the maximum of the exponential growth of the top block or the bottom block? And that's in there.
Yeah, I mean, it's not hard to, it's a lemma in Furstenberg Kiefer, but it's not, it's tricky. And it uses IID, if I'm not mistaken. But I didn't go into understanding where IID is used. And just one remark, since you're asking, just let us take, I mean, yeah, I know we have this in mind. I mean, yeah, the exponential growths are 0, but this goes to infinity, but at the exponential rate, it's 0. This is what it's saying. 1, 1, n, and okay. And okay, so remark f of v mod f is 0, which means that down all the vectors grows in the same way. So I will have a stationary by the case 1, I will have a stationary probability measure on the projective space of the quotient, which will have the good Lyapunov exponent. But why does it come from a probability measure? So I will just tell you, because I'm just aiming you a construction of a stationary probability measure, and let me tell you how can you construct it. Take now V not in F, take a limit point of this zero mean, V not in F, good exponential, top exponential growth, and K and this will have top Lyapunov, this will have a cocycle average maximum. And the proof goes down by projecting down, saying that I proved already what happened before, and then going back. I mean, this, it's not a proof, but this is how we can construct. Okay, or, I mean, I definitely can give more details, but I want to move on. Yeah.
The stationary measure has something to do with the stationary measure of the action on the quotient?
Thank you. Okay, so it will take time. So, yes, and this is abstract. So there is a, yeah. Okay, for sure, if you project this, okay, let me just say.
So on the quotient, you don't have F, so you already have.
We have an equivariant map.
Okay, yeah.
And this induces an action on PV not F. Now, I can project everything. If I say this exists for sure, its projection is stationary.
Yeah.
But the natural question is, from the inverse, I have a new bar. This is my initial data, a probability measure on V mod F, mu stationary. Can I lift this one? And yes, and there exists a unique lift. So this is part of the things I proved with my co-author Gregory. Yeah, it's a bit a precision of Furstenberg-Kiefer. If I have nu, there exists a unique lift. So maybe I have uncountably many stationary ergodic ones, and each one you can lift. And in particular, if this I have a unique, I have unique. So there exists mu stationary nu such that on PV. And what is V? RD. Thank you. Okay. Example just about F non-zero, what kind of situation it's happening in this reducible setting, just to motivate. The natural generalization of this one thing comes from a fine iteration, a fine IFS. And lambda less than 1. What lambda less than 1? What happened when we do the product? Okay, lambda less than 1. So what is the top Lyapunov exponent? It's enough to look here. Okay, it's not a good idea to say A. Sorry, this is A less than 1. The top Lyapunov exponent of my whole thing is the maximum of the exponential growth here. So lambda is the max between len A, which is negative, and 0, so it's 0. So what is F? What is F here? The set of vectors which has exponential growth less than the whole thing is this line invariant line. So, invariant line, and when we do the product, with epsilon I either minus 1 or 1, I will have here
Lambda is A.
Thank you. A to the power n. And a sum here that I can explicit. And this will give me a series. Okay, I needed to say how I'm doing my product. It's very important. It's on the right. It has nothing to do with I'm saying. This is B1, Bn, the opposite direction. And this gives me a series which is absolutely convergent. So it converges to a random variable, and the distribution of the random variable is this is called a Bernoulli convolution, and the distribution of this random variable is called Bernoulli measure? No, I don't know what. Bernoulli convolution. Okay, it's called Bernoulli convolution. But just a remark that this converges almost surely because A is less than 1. And this converges almost surely to a random relation. Not clear what I want to do with all of this. Bernoulli convolution. Is it clear? I mean, I was trying to illustrate what's happening with F non-zero. F non-zero, I have a subspace with lower exponential growth, and here it's a line. Okay, so here I said something maybe not related, but let me make it related. Let us now understand the probability measure on P of R2. Okay. Okay, this is a random matrix product now. And I want to understand stationary, let's say, probability measure on P of on the projective line. I have one fixed direction. I have a fixed direction. And actually, this will give me a measure. It's converging to a random variable. It has a measure. And I will have a compact here. This is, I will have a compact set here. It supports a fractal. And actually these will be, I'm not doing proof, I'm just trying to explain the reducible setting, which is a bit different from other settings. But I will say this next time, just to illustrate.
It will be fractal if A is smaller than 1/2 in absolute value. Otherwise, isn't it? If A is bigger than absolute 1.
Yeah, I said A is less than 1.
Yeah, but 1/2. I mean, if it is less than 1/2, it will be a fractal, isn't it?
I mean, fractal, I mean, it converges, yeah. Okay.
If it is bigger than 1/2, then
it's, yeah.
Exactly 2.5 is the better measure.
Yeah. If 1/2, then it's the
Yeah, but I mean, for me, just a measure, yeah. For less, yeah. Okay, so on P on R2, I have actually two probability stationary measures, a point and, I'm giving the picture, and the distribution of this living in a compact set inside an open set of the projective space of R2. Okay, let us go back to the reduced.
So if I understand, one is not the good one for having the Laguna exponent because it's exactly F and the other is a good one.
Exactly.
Okay,
So,
I understood.
Yeah, exactly. So the Lyapunov, in general, given mu, you have a filtration, deterministic filtration, subspaces which are invariant. Invariant under the group. And dictated by these cocycle average of stationary measures, such that each mu stationary, mu ergodic, lives in some P of Fi minus P of Fi plus 1. And F2 is the first bad one. It's the F, my F. So matrixy speaking, the bad ones are living here, but maybe here also I have bad of bad of bad of bad. F of F, F of F. The stationary probability measures giving the good Lyapunov exponent live on an open space, which is projective minus P of bad. And the question is what they are, for sure. But if it's irreducible, now I have, it's another framework which is interesting, yeah. And just finalize an example of F equals 0, which is not irreducible. Just take AA. Do random walks like that. But in this case, F is reducible, and F is 0. It can be 0 also. It's already interesting. So all of this is Furstenberg-Kiefer, knw, Furstenberg-Kiefer, and independently knw. Okay. What's happened? Some more explanation about. Now my goal is to give a more to detail what I just explained, I want to give a classification of stationary probability measurement, a bit more refined than this. Let me tell you what's known in the irreducible setting. So we'll wait till Friday to explain the reducible setting a bit more. Irreducible setting, so these are works of Benoist, historically Guivarc'h, Raugi, and Benoist. And it starts with Furstenberg. So the irreducible setting, all vectors grows in the same way. This is f equals 0. And, okay. Let us start with Furstenberg. So, the historical. A case of unique ergodicity. So, a very well-known case. Suppose that the semigroup generated by your measure, the semigroup, acts not only irreducibly, strongly irreducibly. I will explain what is this, and more importantly, and proximally. It contains a proximal element. I will explain this. Then, so my initial data is fixed, mu is already here in my initial data. There exists a unique new mu stationary on P of RD. It's called the Furstenberg measure. What? And the yes. Acts. And the works of Guivarc'h and Raugi consists of understanding what's happening without the proximality assumption that I didn't define yet. So strongly irreducibility, SI, means not only that you do not fix a proper subspace, you do not fix a finite union of proper subspace. No finite union fixed, global. So the example of Furstenberg, the Kiefer counter example is not here. Because it's irreducible but not strongly. It permutes E1 and E2. So I don't want to deal with periodicity assumption. Strongly irreducible. This is an algebraic assumption. Proximality is really dynamic. Proximality means gamma is proximal if and only if it contains a proximal element. So the semigroup is said to be proximal if it contains a proximal element, which means what? Which means that it has a simple eigenvalue in modulus. The spectrum of gamma is consisting of lambda 1, let's say lambda 2, convex, with lambda 1 bigger than lambda I for any I, and necessarily this lambda 1 should be real. Because my matrix I. Dominant eigenvalue. So I want to exhibit a hyperbolic behavior in some sense, because what's happening here, remark, gamma proximal, I look at, maybe I have some size issue. I iterate my transformation and I look at it projectively. It will converge to a rank 1 projection on the eigenvector of the biggest eigenspace. a rank 1 matrix. It's a rank 1 matrix. And it's because by Jordan decomposition, you will have lambda 1 and things here which are bad. Jordan, or I mean, generalized eigenspace decomposition, these are bad. And when I normalize by the norm, by Gelfand formula, this will be killed at the exponential root. So just
to one, no? I mean that. No,
above here,
yeah.
lambda. I mean, I do not have eigenvalues like 1, I, no. That's what's it? Okay.
Okay. Then the one
Yes.
is different to
To one.
yeah. You write two different to
Thank you.
Excuse me.
Yeah.
Shouldn't it be excluded that this rank 1 matrix is not nilpotent?
That's why I said rank 1 matrix. It can be nilpotent. Did I say something wrong? It can be nilpotent. Yes, it can be nilpotent. This is correct. And these one in norms may be bigger, but by Gelfand formula, I'm dividing by the norm.
Yeah, I mean, yes, so I just don't understand something. So if I just know the property that this gamma n power goes to a rank 1 matrix,
Yeah.
then it still can be this 1, 1, 0, 1 matrix.
You mean at the limit?
Yes. No? So if I choose gamma to be 1, 1, 0, 1, and I normalize it by its norm?
Yeah, you will have at the end this.
Yes.
So yeah, you're right. That's why I felt there was something, so I didn't write any more projection. But yeah, you're right. 1 divided by its norm, which is 1, which is 0, 0, 1. So it's rank 1, but it's nilpotent. So what's wrong?
Yeah, but then if this is my only matrix, then it's not proximal. That is not proximal.
But that is not proximal. We agree. This is I think this is correct. It's a projection.
Yeah, it's a projection.
Yeah, this is a projection.
Okay.
Yeah.
Oh, yeah, okay, rank 1 projection. Sorry, I thought that's rank 1 matrix. Okay.
Rank 1 projection.
Rank 1 projection. Okay, yes, okay.
Okay, so rank 1 matrix, and it's a projection. Sorry, I'm sorry for the confusion. It's a rank 1 projection. That's correct. I'm short of time, right?
Yes, you are. It's the time, yes.
Okay, so just example, just to say that the example of SL2Z. So I take a generating set of SL2Z. Take any probability measure.
SL2Z.
Take any probability measure with support S, then this is verified. I have many proximal elements in SL2Z, even if my generating set were not proximal, and it acts strongly irreducible. And this example, we're saying that there is a unique stationary probability measure. for any mu. So yeah. So this probability measure depends on mu, but I will explain next time that its support does not. Thank you.
Questions? So, no questions? Thank you again.
Thank you.
I hope only
No, I'm not happy to.
they have opened doors speaking. Actually, the discussion.
No, I'm not happy to.
There was somebody.
Sorry, I just missed when you say.
No, because I was
projection.
also lost when I was writing.